Okay, I'm going to work 16.2 now. We've got a motor system up here with a wheel attached or pulley attached to it, and another larger one. And this could be driving anything. This could be driving your engine, driving your alternator, or any of its other accessories. Any scenario you can think of, anything attached by a pulley. Something that's very interesting, we looked at gears in the last lecture video of 16.3, and how when you have gears, let's not use highlighter color, when you have gears and they're touching, that they have the same velocity, the exact same velocity vector. They do not, however, share the same acceleration vector. They have the same v squared, but they don't have the same r. So the tangential might be the same, but they have a different radial component, giving them different vectors. And so for velocity, they have the same exact vector. For acceleration, two gears do not. Okay, well, we can think of a pulley system as the same exact way. If I look at this point right here, at any given time, it is moving at the same exact speed as this point, as this point, as this point, and you need to wrap your head around that to solve these problems. The velocity of the pulley is the same everywhere. Now, this one's going to spin a whole lot faster than this one, and we'll figure that out and be able to see that. Okay, so we know radius A, this is A over here. We know radius B, 0.4 meters. It says it rotates from rest, and it is a constant. So we're going to use constant acceleration formulas. Angular acceleration of 2 radians per second squared. Find the magnitude of the velocity and the acceleration, not angular acceleration, regular acceleration of this point P right here. So it's going to have some velocity vector like so, but it's going to have a radial component as well as a theta component or transverse component as it rotates there. So we'll figure that out. But all we have to start with is alpha and the two radiuses. I bet I can figure some other information out from that. And they want to know the velocity and acceleration after 2 revolutions, or 4 pi radians. So let's use 4 pi. Okay, since alpha is constant, we can use constant acceleration equations. I'm going to figure out what omega A is. What A is spinning over here, this is our driving motor. I'm going to figure out what the angular velocity is after 2 revolutions. So we got omega final squared is equal to omega initial squared plus 2 times that constant alpha that we have, alpha A, times theta final minus theta initial. This was 0. This was 0 also, so omega final of A is equal to, you can come out to be about 7.09 radians per second. Alright, we need that. Since this thing has the same speed everywhere, we can figure out, just like if they were gears, what omega B is. So the velocity of each point, we would say omega A RA is equal to omega B RB. Okay, we know this, and we know that now. Well, we can find omega B, and that comes out to be 2.659 radians per second. We can do the same thing with alpha because we were given alpha as constant, so alpha is not going to change. We can say alpha A RA is equal to alpha B RB. And alpha B is then equal to 0.75 radians per second squared. Okay, we need this number, we need this number, we need that number. Because when we're looking at the velocity, let's take care of the velocity first. The velocity of point P, that thing right there. The velocity of point P is going to be tangent to the path, and we can say it is equal to omega B RB. We now have omega B right here, so we can calculate that to be 1.06 meters per second, because we're looking at linear velocity. Alright, there's one answer. We need to find the two components of acceleration, though. There's one in the normal direction and one in the tangent or transverse direction. I think your book uses tangent for this section, or for the specific problem. So the acceleration in the tangent direction is just equal to our alpha B RB. Well, we know alpha B now, and RB was given to us. We can calculate this as 0.3 meters per second squared. Meters per second squared, not radians per second. And we need the normal component at point P. Well, in this, we know V, we could do V squared over R. That's the same thing as omega crossed R, or omega R, if you want to check out those units. And what we're going to get is 2.827 meters per second squared. Now, we need to take these two components because tangential component is like this, the normal component is like that. We need to figure out the magnitude is what it asked for. And y'all know how to do it. It's the square root of 0.3 squared plus 2.827 squared. So get a magnitude of the velocity right here. We get a magnitude of the acceleration as 2.84 meters per second squared. Thank you.